guess that this first lecture and this first medal was like advanced physics and chemistry for cement materials, which of course is a very important material for RILEM. The next lecture is about something very different, but we are happy to see in the previous years that in RILEM we have a growing contribution of people dealing with cultural heritage. And this is a domain of science and technology that we didn't know that much some 2 decades ago. And we are realizing every day now that we have some very common points and very common topics with this community. So I'm really happy that this year one of the medal is given to something very representative of RILEM historical activities, and that the second medal is given to something that is quite new in our community. So Enrico, the floor is yours.
Thank you, Nicholas. Thank you, everyone, for being here, and thank you to RILEM for giving me the opportunity and the reason for giving this presentation. So my presentation will be about phosphate-based treatments for conservation of stone. So first of all, why are we interested in stone conservation? So the first reason they may come to our mind is because of the economic profit that we can get basically from tourism. But still, I would say that an even more important reason is because cultural heritage and stony cultural heritage is a very important means by which we can preserve our identity as a society, as ISIS unfortunately demonstrates. So among the stones used in cultural heritage, the most diffused ones are carbonate stones, so mainly marble and limestone. So these two stones have basically the same mineralogical composition, that is basically calcite up to 100%, but what is significantly different between these two lithotypes is the porosity, the microstructure. So marble is basically non-porous, so it has very tightly packed grains, while limestone may have a porosity up to 40–50%. As a consequence of the different microstructure, also the deterioration processes that these two stones undergo are quite different. So in the case of porous limestone, the deterioration processes are probably, are more similar to those that occur in other porous building materials, such as concrete, so mainly stress arising from crystallization of ice and salts inside the pores. While in the case of marble, being non-porous, we have basically different with deterioration processes. So one is the so-called dissolution of calcite, the dissolution of marble that arises from the relatively high solubility of calcite in water. And this is important because it can lead to a so-called surface recession of a few millimeters per century, which implies a loss of carved elements on the surface of marble elements. At the same time, just because marble is non-porous, so it's highly sensitive to another peculiar phenomenon, which is the so-called thermal deterioration. So because calcite crystals behave anisotropically when they are subjected to temperature variation. So repeated heating cooling cycles, meaning day-night temperature variations, so they can cause the opening of microcracks at the boundaries between grains, which give rise to the so-called sugaring, which means that calcite grains literally fall apart, fall down, and the spectacular bowing that affects both, in this case, gravestone in a cemetery in Paris, but also slabs used for cladding new buildings. So the basic aims of material science applied to stone conservation has these two, so developing suitable protectives and suitable consolidants. So protectives are products, materials that are aimed at bond tightly to the substrate and creating a surface layer, a surface coating that has a lower solubility than the substrate, so that this layer is able to provide protection against the dissolution in rain, especially acid rain. While consolidants are products that are aimed at penetrating into the stone, into the pores, in the case of limestone, for instance, or in the microcracks that develop in marble, and then by reacting with the substrate to bond the grains, so has to reestablish cohesion between grains and increase mechanical properties. Unfortunately, at the moment, all the products that are available in the market, which are basically silicate consolidants, lime-based consolidants, and polymeric consolidants, they all have limitations when applied to carbonate stones in terms of either efficacy, compatibility, or durability that are the main requirements that this product must meet. That's why in 2011, we started investigating the possible use of a new material, a new mineral, hydroxyapatite, HAP, as a possible mineral to preserve stones. So hydroxyapatite is a calcium phosphate salt that is basically the main constituent of our teeth and bones. And the reason why, following an idea by Professor Scherer at Princeton University, we started investigating the use of hydroxyapatite. So why this mineral was identified as a potentially good candidate for achieving these goals. First of all, because, as you can see, hydroxyapatite has a much lower solubility and a much slower dissolution rate than calcite, which of course is good to provide protection. And at the same time, it has a quite good match in terms of crystal structure, being rhombohedral for calcite and hexagonal for HAP, and a quite good match in terms of lattice parameters, so that at the beginning we hoped that epitaxial growth of HAP crystals could take place over calcite. Based on biomedical literature, because as I mentioned, hydroxyapatite is widely studied for bone regeneration and tooth preservation, let's say. So it is possible to form hydroxyapatite in green, starting from calcite, calcium carbonate, by reacting calcium carbonate with an aqueous solution of a phosphate salt, so that in the end the calcium ions come from the substrate and the phosphate ions come from the solution that we treat the stone with. And what is formed is, in theory, stoichiometric hydroxyapatite and some volatile byproducts that do not remain in the stone and so aren't harmful. Of course, this is the basic idea, and since 2011, we have been investigating, and this is partly still in progress, all the reaction parameters to optimize the treatment, so in terms of nature of the precursor of the phosphate salt to be used, its concentration, the best treatment duration, the possible influence of pH, the effects of adding ions or organics to the solution. So the first part of our studies, by, let's say, our group and also others that started investigating the same treatment, was to identify the best treatment parameters. So in terms of the salt, the precursors to be used, so attention since the beginning focused on ammonium phosphate salts. This is because of the volatility of ammonia, so that nothing remains into the stone, because otherwise, if, I don't know, some sodium salt would be used, this sodium or other elements could be incorporated in the hydroxyapatite lattice, thus altering its properties. Then in terms of among the different phosphate salts that could be used, you can see some examples here. So in the end, we found out that it's basically irrelevant what phosphate salt is used as long as pH is controlled, because it's pH that controls the amount of phosphate ions intended as PO4 3- that are available, because these ions are the ones that are needed to form hydroxyapatite, while, for instance, HPO4 are useless in our case, not to say counterproductive, because other phases, such as brushite or calcium hydrogen phosphate, may form. So in terms of pH, this has a very strong influence, as you can see, using the same concentration, the same salt, by simply increasing the pH from 8 to 10. So quite a lot of new phases, new material form, but this turned out to be heavily cracked. So in the end, our attention focused on almost neutral pH values. Then another important issue was the possible addition of ions, in particular calcium ions. And we found that by providing calcium ions from the exterior, so that in the end they are not only coming from the dissolution of the substrate, but they are already available in the solution. So this strongly helps formation of a continuous coating on top of calcite, on top of marble, which is what we wanted. So in this case, you can see the difference by using a 1 molar DAP, which is diammonium hydrogen phosphate, with and without addition of 1 millimole of calcium chloride. Then also the nature of the calcium source to be added was investigated by screening between different salts, so for instance, calcium chloride, calcium hydroxide, and others, and in the end, calcium chloride was found to be the one providing the best results in terms of surface coverage. However, the addition of calcium ions into the solution, so it also has an impact on the nature, on the mineralogical composition of the new phases that form. This is very important because HAP was identified as a very promising mineral because of its very low solubility. In case calcium phosphate phases form which have a higher solubility, this could be a serious problem in our case. So we found that when we add calcium ions to the solution, we form both HAP, hydroxyapatite, and octacalcium phosphate, which is a different mineral, of course. As you can see, it has a higher solubility than HAP, but still a lower solubility than calcite, so it's still positive to form for our aim of protecting marble. But let's say that generally speaking, so the nature of the phases that form, it's a very important and tricky point because, as you can see, half a dozen of different phases may form, and in case very soluble phases form, such as monocalcium phosphate monohydrate, which has a solubility of 18 grams per liter. So if we form this phase, this would be useless for our purpose. So different groups, apart from ourselves, so started investigating the effect of different treatment parameters on the nature of phases that form. So for instance, some colleagues from Milan in Italy, so they used micro-Raman to also try to identify, so starting from calcite surface, if there's a stratigraphy, so a sequence of phases that form. And of course, this was found to be the case, but this strongly depends on the specific treatment conditions that were investigated, so in terms of concentration, pH, and treatment duration. So the duration of the treatment is important as well. So as you can see, we found that basically after only 24 hours of reaction, so we get a complete coverage of marble, which is positive because for, let's say, the standards of stone treatment, so stone consolidant, 24 hours is a very short time because the most widely used consolidant, which is the ethyl silicate, takes at least 4 weeks to complete its hydrolysis condensation reaction, so 24 hours compared to 4 weeks, it's a very short time. So we also checked that the development of mechanical properties in terms of consolidating ability, so its progress over time, and as you can see, we found that basically after 48 hours, the mechanical improvement is already 90% of the one that we get after 8 days. So this 24 hours was identified as the ideal treatment duration. Here you can also see the influence of the precursor concentration. So generally speaking, the higher the concentration, the higher the consolidating effect that we get. However, the higher the concentration, the thicker the layer that forms on top of calcite, and this is potentially a problem because a higher thickness may lead to cracking during drying of the coating. And as we were recently able to observe also by focused ion beam in cross-section, so the layers, the coatings that form in these conditions are also porous, which of course is a problem because micro cracks and pores may allow rain, so the acid, to reach the substrate, which would be bad for our purposes. So to avoid this problem, So to reduce the thickness of the layer, reducing the concentration is a potentially good way, because if we are able to create a layer that is as thin as possible, so because of thermodynamic reasons, it would be impossible for this layer to crack. So we tried reducing the DAP concentration, but at the same time we needed something to improve the coverage and favor HAP formation. And we found out that adding ethanol, so alcohol, has a very strong effect. So as you can see, at the same very low DAP concentration, by increasing ethanol concentration, we were able to obtain a continuous coating. And also in terms of the coating microstructure and density, so we were able to get a thinner layer with a significantly better density by adding ethanol to the solution. And so as you can see also the interface between calcite in the bottom part and the new phosphate phase, so the presence of pores is highly reduced, which is positive. So why is ethanol beneficial? So we started investigating this in the literature, and basically what we found, what we think at the moment, is that ethanol, alcohol, has a positive effect because its molecules are able to weaken the hydration shell of the phosphate ions in the solution. So in our aqueous solution, we have the phosphate ions that we provide. They usually are surrounded by water molecules in a more or less ordered way. So when we add ethanol, so these ethanol molecules are able to, in some cases, substitute for water molecules, in this way making the ions more reactive and thus facilitating HAP formation. However, ethanol is also reported to have another effect that in our case might be counterproductive, which is being absorbed onto calcite surface, which means that the ethanol molecules orient itself with the hydrophilic part towards calcite and the hydrophobic part towards the bulk solution. And this may be a problem because this may limit the speed and the reactivity between the substrate and the solution. This is why we have recently started investigating, the possible use of alternative solvents that have the positive effect in the solution, let's say, without having the problem, in our case, of being absorbed onto calcite surface. To do so, we thought that measuring the amount, the concentration of phosphate ions in the solution could be a good and relatively, rapid way. So we started, the first thing that we tried, that we thought about, was using isopropanol, IPA, as a because of the bigger molecules as a possible substitute for ethanol. And what we found was that in terms of PO4 concentrations, so 10%, an addition of 10% IPA basically corresponds, so give us the same amount as phosphate ions at 30% ethanol. So IPA is proved to have a much higher, stronger impact than ethanol, which led us to compare one bottle of Indian Pale Ale with 3 glasses of ethanol wines. So we moved on testing IPA as a solvent to be added to our solution, and we found out that the density, I'm not sure if it's possible to appreciate from these pictures, but anyway, so the coating that forms is much denser, and also at the interface between calcite and the new phases, it's basically quite hard to identify a sharp interface, which is good. So with all of this in mind, we started investigating the effectiveness of our treatment. So first of all, in terms of ability to protect marble. So we tested the marble protection by a simplified system setup, which is exposing our samples to a simulated rain, which is basically a nitric acid solution initially at pH 5, and then we measured the pH increase over time. As you can see in the case of the untreated samples, so pH increases over time because hydrogen ions are consumed as calcium ions are extracted from, are dissolved from marble. So this is the untreated sample. Then, as a reference, we tested ammonium oxalate, which is the commercial treatment, so nothing developed by us. And as you can see, the results were not so good. So we thought, okay, so maybe we can do better. And this was the case because let's say that starting from the treatment with simply DAP and calcium chloride, so with no ethanol addition, a quite coarse, quite porous microstructure. So we were able, unfortunately, not to completely inhibit marble dissolution, but still to delay it quite a lot. So let's say that for reaching the same pH level, it took basically twice as long. So we were able to provide our marble, our monument, with a good increase in durability. We got better results when we started, investigating using the formulation with also ethanol addition, and slightly better results when we use IPA. Anyways, as you can see, after some time, 6 hours, so all the curves kind of reach the same point, so they're not so different. Why is this the case? Because in the end, even if we can get a quite good coverage of marble surface by all the means that I mentioned, still looking closely, so there are some grains that are completely bare. So for instance, in the right image, even if all the surrounding grains are perfectly covered with HAP, and so in other cases on the left. And so the problem in this case, we think, is that the orientation of the calcite crystals have a very strong influence on the possibility of HAP, of hydroxyapatite, to grow on top of these grains. So according to literature, people were able to get epitaxial growth of HAP on top of calcite, but this could only take place for very specific orientations of both minerals. But unfortunately, in our case, because we are not working with a single crystal of calcite, but we have hundreds of crystals with random orientations, so this is unfortunately not always possible. So for those grains that have the least favorable orientation, so it's at the moment quite hard to get a sufficient covering. And this is why if we observe our coatings after the acid attack test, so we can see that the acid was able to produce some microcracks, and in some cases to decay, to worsen our treatment. And this is because starting from this bare area, so the acid is able to reach marble and then act as the interface between the substrate and marble. So we are currently working on this to improve the ability to cover grains, so to nucleate hydroxyapatite also on calcite grains with the least favorable orientation, and we hope that by screening additional solvents, we will be able to improve this part. Then moving to the consolidation of marble, so consolidation meaning the ability to bond grains and reestablish mechanical properties. So this is the main aim of a consolidant. This function must be carried out without altering the color of our marble, because otherwise nobody would accept it if our monument would turn yellow starting from a bright white. And it is important that also stone behavior, especially in the case of marble, in terms of thermal behavior, is not altered after the treatment, because if we make the stone more susceptible to decay after our intervention, of course, this is something unwanted. So to do so, we started working on artificially weathered samples in the lab, because, of course, we cannot spoil good samples coming from real monuments for our first trials. Then we moved on to naturally weathered samples, and finally we did some pilot application to real artifacts. So to produce artificially weathered samples, as I mentioned, we exploited the anisotropic thermal behavior of calcite crystals, so which makes us able to produce damage by heating samples at high temperature for a certain time. To find out at what temperature and how long should we heat our samples, and if it's possible to create a gradient in marble properties, which is usually the case in the field. So we started analyzing some real samples coming from a decayed gravestone, in this case in Bologna, and we found out that the decrease in mechanical properties in terms of dynamic elastic modulus measured by ultrasound is about 30%. So then we developed a mathematical model that allows us to predict, starting from the solution the situation that you can see on the left, so a piece of marble placed on top of a hot plate. So for how long and at what temperature we should heat it to reach a certain level of damage that we want to achieve. So to achieve the same level of damage that we found in the field. So we found out that by heating at 200 degrees for 20 seconds, this is, based on the model, sufficient to get this level, this decrease in the first centimeter of the stone, leaving the other part undamaged. And this is important because this is the condition in the field where you have the marble surface that is exposed to solar radiation that is more decayed, while the underlying parts are still sound. So then we tested our treatment, and as you can see, so starting from undamaged marble, we first carried out our own artificial deterioration, and we got a 39% decrease in dynamic elastic modulus. And then by treating our stone, then once we got a significant improvement in mechanical properties, and after the second treatment, we basically got the mechanical properties completely restored to the original condition, and also it is important without causing over-consolidation of the sound part. This was made possible by the formation of the new mineral, HAP, inside the micro cracks between grains. So this new mineral was able to bond the grains and improve mechanical properties. As you can see also from this fib cross-section, where you can see the new phases forming inside the microcracks between the grains. So then we investigated different levels of deterioration, so by heating, for instance, at 200s rather than 300s. So in this case, we reached a more significant level of decay, meaning more cracks with bigger size. And then we compared our treatments, again, with commercial treatments and different formulations. And as you can see, in terms of simple mechanical improvement, our first original formulation, so the one with a coarse, porous microstructure. So in spite of being porous, so not being able to provide a good acid resistance, so still it was able to very strongly improve marble mechanical properties, and this is because it's easier for this formulation with a higher concentration to fill the cracks and improve mechanical properties. So let's say that depending on the goal that you want to achieve, whether it's more a mechanical binding effect or acid protection, so one formulation may be preferable over the others. Here, that's the figure that is missing, which was the, okay, there are several figures that are missing, but were originally present. So in this slide, originally, there was the thermal behavior after the consolidation, and so we could find that our treatment does not increase the residual strain of marble after treatment, which is important because with some commercial polymeric treatments, it was found that after consolidation with these polymers, the thermal behavior of marble got worse, which of course is undesired because as soon as the thermal cycles start, all the benefit is lost and marble undergoes a faster decay. So, okay, if we have this kind of problem for all the remaining part of the, okay, we are back. Sorry for the interruption for the commercial break. So, after doing all these preliminary tests on the artificially weathered marbles, so we moved on to some naturally weathered marble, as you can see in this picture. So we carried out the treatment. We found that, again, by ultrasound that are not destructive, the mechanical improvement was satisfactory. What was interesting in this case was that the phase composition, so the mineralogical phases that we found were slightly different than in the case of the artificially weathered samples, meaning that in this case, we only found hydroxyapatite, which is the mineral that we actually wanted to form, and while no octacalcium phosphate and no tricalcium phosphates were found. And we think this is a consequence of the fact that starting from the original conditions, so a black crust made of gypsum was originally present on top of our samples, so we carried out some cleaning, but still some gypsum, so calcium sulfate, hydrate was present, some residues were still present on the surface. And because gypsum is much more soluble than calcite, so it's able to provide some additional calcium ions for the reaction with the phosphate solution. And this proved to be beneficial for the formation of the new phases, so that only HAP was formed. Starting from this, we also carried out some preliminary applications in the field on gravestone on a tombstone in Bologna. So we treated one base and one element in the basement of this tomb. So by carrying out the same procedures that I explained, and then immediately after the treatment and after 1 year, just to check the durability, so the relatively long-term effects of our treatment. So we found that still good mechanical improvement was present, and that the variation, so the color change, so the modification of the aesthetic appearance was below the threshold that is usually accepted in the conservation field, which is, of course, positive. So starting from this, in the next few months, we should also carry out a couple of pilot applications to real sculptures in the Versailles Palace in France. So these are the two lucky candidates that are going to be treated, so hopefully we won't spoil them. Then coming to the final aim of our, let's say, research, which is consolidation of limestone, so a porous matrix. So again, the aim is to improve mechanical properties without altering the color of the stone. And in this case, being a porous stone, what is most important is that our treatment does not alter the porosity and the pore size distribution in such a way that ice and salt crystallization may become more relevant issues. So we started investigating different applications techniques, so those that are usually applied in the field, so brushing, poulticing, and immersion. So we checked the penetration depth of our treatment, which is a very important aspect, because our treatment, our solution needs to reach the sound substrate, which might be a couple of centimeters below the surface. And we also observed that after the initial applications, over time, there's a redistribution of the consolidant in the pores, so when it's still liquid, takes place. And this because the liquid, the solution migrates towards smaller pores over time. And this is important because it allows an increase in the penetration depth over time. In terms of mechanical properties that we measured by ultrasounds and by tensile splitting tests, so also in comparison with the ethyl silicate, which is the most widely used consolidant in the field, so we were able to reestablish the original mechanical properties, as I mentioned before in the case of marble. We didn't cause any dramatic color change, which of course is positive, because although being slightly, detectable by human eye, still the color difference is below this threshold that I mentioned for conservation treatments. And then coming to the alteration of the microstructure, as you can see, so our HAP treatment in red only slightly reduces the total open porosity. However, it causes a shift towards smaller pores in a certain range. And this is because, as you can see on the right, so bigger pores were partially filled by our consolidant, so that two smaller pores were formed in place of our former one big pores. And in the case of TIO, so ethyl silicate, our alternative treatment, so a more remarkable pore occlusion took place. So we first started testing the effect in terms of durability to freezing-thawing cycles, and we found out that in spite of the initial benefit of using ethyl silicate for consolidation, so over time we found out a decrease in mechanical properties after consolidation of this alternative treatment. And actually the only sample that failed, so it fractured spontaneously, was a sample treated by this alternative consolidant, while our consolidant in red, so it basically remained stable over the cycles, which is positive. So from this, we got an indication that the alteration in pore size distribution by our treatment are not so negative. And fortunately, we also found a confirmation in terms of resistance to salt crystallization. So we carried out some sodium sulfate resistance crystallization cycles. So as you can see on the right, 2 untreated samples and 1 sample treated with this other alternative consolidant failed over the cycles, while our treatments, so samples treated by our treatments, were able to reach the end of the cycle without fracturing. And also, again, in terms of mechanical improvements, so increasing tensile strength, the initial benefit of this alternative consolidant is basically lost. So in our case, because the alteration in pore size distribution were such that no dramatic increase in micropores, so which could worsen the resistance to ice and salt crystallization, because as I think everybody knows, the smaller the pore, the higher the crystallization pressure. Still, our treatment was able to resist these cycles in a very good and promising way. Another important feature of our treatment is that it leaves the stone hydrophilic at all stages. So whereas it is the case of commercial treatments mostly cause an initial phase of hydrophobicity in the stone. And this is potentially a very important issue because if also evaporation of water vapor from the stone is inhibited or anyways slowed down significantly, this may be a problem in case water or salt solution are coming from below the treated surface. So when the treated surface is hydrophobic, as you can see in the square in the top part of the slide, so detachment, so let's say failure of the intervention may take place in case water and water vapor diffusion out of the stone it's prevented. This is not the case of our treatment, so this is another positive feature of this phosphate-based consolidant. So summarizing, our hydroxyapatite treatment was able to significantly prevent marble dissolution to provide a good consolidating ability for marble and for limestone. We are confident to be able to further improve the performance by screening alternative solvents. And anyways, our treatment has several advantages over the commercial available ones. So in terms of speed of reaction, penetration depth, absence of any toxic, dangerous chemicals for both the environment and the operator, which is important. And because of the very limited alteration in stone transport properties. So the work that we and also other groups are carrying out at the moment, so it concerns additional deterioration phenomena of marble, so especially in this very month. So I am working in Göttingen in Germany to see if our treatment is able to arrest the bowing, which is, as you may see, literally the bowing of thin slabs that were used both in cultural heritage, but that are also often used for cladding modern facades. And this is a very important issue also for modern architecture because, for instance, on the very right, you can see the Amoco building in Chicago, which is relatively famous in our community because a few years ago, so slabs started to bow and fracture and fall down from the top of the building. And so they had to completely substitute all the slabs clad in the facade, which cost as much as $65 million. So I'm sure that if we are ever able to stop this phenomenon, people would be interested about it. Then the community is also now investigating the effects of this hydroxyapatite treatment on a variety of substrates, so starting from gypsum-contaminated marble, but also gypsum stuccos. And this is an important aspect because, as I mentioned, gypsum, as you well know, is more soluble than calcite, so more calcium ions are available for the reaction. So this needs to be, so the treatment needs to be tailored for this specific substrate. Similarly, we are also investigating the effects of applying the treatment to stone, limestone that contains salts inside the pores, which is usually the situation because even if salts are removed before the consolidation, not a complete remove is mostly impossible. So people at EtOH in Zurich are now also investigating the effects of applying the treatment to dolomitic marble and magnesium-containing limestone. This is an important and tricky part because we found out at our own expenses that when magnesium is present, so not only or not mainly calcium phosphates form, but magnesium phosphate may form as well. As you can see, a very big crystal on the right. And this is a problem because this may prevent the consolidating calcium phosphates to form. People at EtOH in Zurich are also studying the effectiveness of this treatment on clay-bearing sandstones, which is a very important and tricky substrate because these clays swell, so increase in volume when they are in contact with water. So, and again, traditional consolidants are unable to stop to make these stones resistant to this kind of weathering phenomenon. So hopefully our treatment will be able to do so. Then people at UCLA are studying the effectiveness of using this treatment also for wall paintings that have basically the same type of metric, so a calcitic metric, but also the presence of carbonate or silicate aggregates, and also oxides that were used as pigments, so that's an additional factor to take into account. And also recently for archaeological bones, which is another interesting aspect because bones are mainly made of hydroxyapatite, so using hydroxyapatite to consolidate hydroxyapatite would be the perfect fitting match. And we are now also starting to use more advanced refined techniques to find out the effectiveness, so for instance, the distribution and the penetration depths of our treatment. And then finally, I think it's quite positive and good opportunity for us that nowadays, several groups around the world, and especially in Italy, I've started investigating this treatment, which means that also some fruitful collaboration can be established between different groups, which is positive. So to conclude, I would like to thank Professor George Scherer at Princeton University for giving me the chance to start working on this topic since the very beginning in 2010. Then Dr. Elisa Franzoni and Dr. Gabriela Graziani, which are my colleagues at the University of Bologna, and I've carried out most of this work in collaboration with them. And Sonia Naidu with now a PhD. She was working in Professor Scherer's group when I joined the group in 2010. So again, we did some work together. And then finally, I would like to thank the European Commission that is funding my activity in these 3 years through the Marie Curie Action, the Marie Curie Project, HEP for Marble. So this is all. Thank you all for the kind attention. If you have any questions, please.